It's been called the quiet workhorse of space science, a means of transporting ambitious and hefty scientific experiments to the edge of space.
Gonna start inflation at this time. Everybody got earplugs that wants them?
While the technology may seem old-fashioned, it remains the quickest and most cost-efficient avenue to near space.
When you compare to satellite missions that take 5 to 7 years to develop and millions of dollars, scientific ballooning can be done on a fraction of that budget and in a fraction of that time.
But what are the challenges of launching this experiment called BLAST? A scientific payload designed to look back in time billions of years. One of the most sophisticated balloon-borne experiments ever attempted. After years of detailed design and commitment, on top of weeks of preparation in one of the world's most remote locations, success hinges on one uncontrollable factor.
The biggest enemy out here is the wind.
I think it's going to smooth out.
We sat and watched the wind blow for days.
Travel to the ends of the Earth, where the passion of scientific discovery
We need to launch within a matter of days.
and better judgment collide.
Some of the second guessing and looking at the anemometers and all that stuff, that really doesn't serve any purpose.
From the study of the atmosphere to the origins of the universe, it's been the vehicle for some of the most significant scientific discoveries of our time. And the future holds even more promise for one of the greatest scientific stories never told.
One of our favorite scientists described the first balloon launch he ever saw as a beautiful ballet that was orchestrated with military precision. By guys in dirty blue jeans. We issued flight line uniforms shortly after he made that comment.
No one launches more scientific balloons from more places around the world than NASA's Columbia Scientific Balloon Facility based in Palestine, Texas.
The strength of the program is that we can fly very heavy payloads, up to 8,000 pounds, and very large payloads. We can put those experiments into near space above 99.5% of the Earth's atmosphere.
The scientific balloons they use are made of an incredibly thin polyethylene film, only 0.02 centimeters thick, the thickness of an ordinary sandwich bag. They can fly that 8,000-pound payload, the weight of 3 small cars, nearly 23 miles high, to an invisible ceiling where the atmosphere ends and space begins, and can stay there, riding upper atmospheric winds for up to 6 weeks. Due to the natural difference in density between the helium gas used to fill the balloons and the air, as these zero-pressure balloons ascend in the atmosphere, they expand to volumes of up to 40 million cubic feet, nearly the size of a stadium like the Louisiana Superdome.
But to launch those into space would take a very expensive launch vehicle. I mean, really, literally on $100 million for the launch. And whether we do these for, certainly 1/100th of that or less.
And we can have greater access to space, more frequent flights of science, and in the end, the scientist gets their payload back.
From New Mexico to Arctic Sweden, and Australia to the coldest and driest continent, Antarctica. The Columbia Scientific Balloon Facility launches 15 to 20 balloons a year, over 4 to 5 campaigns.
All right, guys, we're ready.
Locations are typically dictated by science or longer data gathering airtime.
Any science that can be done above about 99.5% of the Earth's atmosphere, either looking up or looking down, can be done on balloons.
The most emphasis we've had over the last few years has been in the field of cosmic ray astronomy and what's called cosmic microwave background astronomy, which is origin of the universe type work. That's where we've done our most remarkable work over the last 10 years.
The scientists using scientific balloons include some of the world's most seasoned researchers and university professors, even graduate students.
The young scientists can design the experiment, build the experiment, fly the experiment, and analyze the data, go through all aspects of a space mission, which is not possible with our large space missions.
And ballooning is a vehicle for world-class science. In the mid-1980s, an ozone hole was discovered over the Antarctic continent. The initial measurements were all made from scientific balloons. Another high-profile balloon-borne experiment called Boomerang in 1998 showed the geometry of the universe is basically flat and continually expanding, a finding consistent with the Big Bang Theory. And in 2003, a cosmic ray experiment called CREAM orbited the South Pole 3 times, setting a long-duration scientific balloon record of 42 days at float.
15 years ago, this capability would have been unheard of, and we got quite a bit of attention in the science community from people who are interested in these extended duration flights.
Attention, or more the lack of it, has long been a scientific ballooning hallmark. The first polyethylene balloons were developed in the late 1940s for upper atmospheric research. Later, the U.S. Navy and Air Force, caught up in the race for space, found another use. Manned balloon flights like the Man High and Stratolab experiments of the late 50s and early 60s played a key role in early development of the U.S. space program. Stratolab 5 was launched on May 4, 1961, from an aircraft carrier in the Gulf of Mexico.
They did a standing inflation of a 10 million cubic foot balloon from the deck of an aircraft carrier that was moving with the wind to create a zero wind condition across the deck of the ship. So you could stand up this 600-foot tall balloon in zero wind conditions.
Aeronauts Commander Malcolm Ross and Lieutenant Victor Prather, aside from being test subjects on the physiology of high-altitude flight, were testing spacesuits designed for the Mercury mission.
The guys are walking out carrying their little air conditioners just like Alan Shepard and John Glenn did, and they got strapped in this open gondola, which is just an open aluminum tubing framework.
Ross and Prather went on to set a human-piloted balloon altitude record of nearly 114,000 feet, a record that still stands today.
But unfortunately, during the recovery process, Dr. Prather slipped and fell in the water and drowned. He had his helmet off, and his suit filled up with water, and he actually would have gone to the bottom of the Gulf of Mexico if he didn't get tangled up in the parachute shrouds.
An achievement and tragedy that managed to elude the headlines.
That flight took place on May 4th, 1961. On May 5th, 1961, Alan Shepard became the first American in space. One day, the space program is ballooning, and the very next day, ballooning died as far as high altitude preparation for space. You know, one day it's balloons and the next day it's spacecraft.
Despite its firm footing below the radar of public attention, scientific ballooning has continued adapting to the times as the quickest and most cost-efficient avenue to space. But are its capabilities up to one of the heaviest and most sophisticated payloads ever launched? While the basics have hardly changed, modern scientific balloon capabilities and dependability have increased exponentially. Evidence is found well north of the Arctic Circle near Kiruna, Sweden, where the midnight Arctic sun brings the snowmelt of summer. and one of scientific ballooning's greatest challenges to date.
BLAST is perhaps one of the most sophisticated payloads we've ever flown.
In a collaboration between the Swedish Space Corporation and the Columbia Scientific Balloon Facility, here at the S-Range Launch Facility in extreme northern Sweden, an experiment called BLAST, or Balloon-Borne Large Aperture Sub-Millimeter Telescope, is being readied for flight. A week-long flight that will take BLAST to the opposite side of the globe, towards northwest Canada and Alaska. A flight that promises the BLAST science team more data-collecting airtime than a flight from the continental U.S.
We're trying to learn about star formation.
BLAST is a very large and very sensitive 2-meter telescope designed to look back in time billions of years, to the point when the majority of stars and galaxies began to form in the early universe.
It's part of putting together the whole story of how do we go from the early universe, which was featureless, uniform, just the simplest gases, into the rich complexity we have today, and how did all those steps come together?
The fundamental concept of cosmology that allows scientists to peer into the past is the fact that light takes time to travel.
So if I look at the moon, I see the moon like it was about 1.5 seconds ago. So let's say something happens on the moon, 1.5 seconds later, we can see it. Or we look at the sun. We see the sun like it was 8 minutes ago. So an event happens on the sun, we don't see it for 8 minutes. Something happens in a distant galaxy that's maybe 1 billion light years away, we don't see that event for 1 billion years. So when I go and look at a distant galaxy, I'm seeing it like it was 1 billion years ago. I have no idea what it looks like now, and I have no idea what it looked like 2 billion years ago, but I know what it looked like 1 billion years ago. Look at a galaxy that's farther away, farther back in time, nearer, more recent.
The hitch is, what they're looking at, early forming stars, are not visible to the human eye.
At optical wavelengths, you don't see stars until they are relatively well evolved and they have dispersed all of the material and the dusty interstellar medium around them.
Everything that's warm, or at least above absolute zero, glows. For example, the sun glowing at 6,300 degrees Celsius, 11,300 degrees Fahrenheit, is an example of visible or optical light. The extremely cold interstellar dust that surrounds newly forming stars measures or glows as low as minus 260 degrees Celsius, minus 430 degrees Fahrenheit. This light or radiation is termed sub-millimeter light. Similar to infrared light, it's a longer wavelength radiation that requires a special camera or detector to see.
So if you're trying to understand the formation of stars and the early evolution of stars, you have to look at stars at a time when they're much younger. And it's at those stages of their evolutionary cycle when they are heavily enshrouded in dust.
Visible light pictures of the Eagle Nebula taken by the Hubble Space Telescope show the interstellar dust. But where are the new stars? The key is looking at sub-millimeter imagery, exactly what BLAST is designed to do.
You want to go look for places, for clouds of dust, where the dust has been warmed up. It's been warmed up by these supermassive, super bright stars that have just formed inside there.
To find these places, the BLAST telescope's primary and secondary mirrors receive and focus light into a cryogenically cooled detector system, where sub-millimeter light is detected at 3 different wavelengths. The data is then converted to a 2-dimensional map of the universe at sub-millimeter wavelengths. From there, BLAST scientists will identify distant galaxies to pinpoint.
To map a 2-dimensional region on the sky, we will scan in azimuth, or essentially just scanning left to right, and then slowly we will be scanning upwards as well at the same time in a certain pattern. We need to be able to point the telescope to about 1/1000th of a degree accuracy.
So we're talking sort of like a gnat's eyelash. We need to know where this thing is pointed to extremely high precision.
Remarkably, blast will be held to this accuracy dangling beneath a balloon, well beyond the Earth's opaque atmosphere. Blast scientists have managed this precision by using a variety of pointing sensors, reaction wheels, and motors, giving blast one of the highest pointing accuracies of any balloon-borne payload to date. As the blast assembly continues, it's important to understand that getting beyond the atmosphere by balloon involves handing complete responsibility for the scientific payload and launch to the Columbia Scientific Balloon Facility crew.
So I'll be communicating with you all the time doing that.
While there are subtle rigging differences from launch to launch based on specific scientific needs, and no matter if launching from Sweden or here in Fort Sumner, New Mexico, the main layout of a typical scientific balloon flight train is essentially identical. This hands-on rigging remains one of the most complex and critically important processes.
We'll set a show time, we'll come out, we'll hang the gondola, then we'll go out to the launch pad.
It begins with the pickup of a scientific payload with a specially designed launch vehicle.
And attached to the payload will be suspension cables that will go upward to what we call a truck plate. That truck plate is actually holding the entire flight system to the launch vehicle. From that truck plate, there will be a suspension ladder that will go over the launch vehicle, and that will connect down to the parachute separator unit.
Rotator should be on.
This unit separates the parachute from the payload to prevent a wind-filled parachute from dragging and damaging the payload after termination. The nylon parachutes range in size from 46 feet to 159 feet in diameter for the largest payloads.
And then we'll have the terminate fitting, which is the link between the parachute and the balloon. That terminate fitting will have an explosive device on it that we'll initiate to bring the balloon down at the conclusion of the flight. And then connected to the terminate fitting will be the balloon itself. And on top of the balloon will be helium valves that will open at the end of the flight as a secondary measure to terminate the balloon.
Meantime, back in remote Arctic Sweden, the blast team knows that while assembling this experiment thousands of miles from home, there are bound to be problems.
It's an incredibly complicated machine.
Setbacks that spark a major time crunch. Could the launch and years of collective effort be jeopardized? As the pace of constructing the BLAST submillimeter telescope quickens, in time to meet very ambitious science goals, the team is faced with the inevitable.
Well, I mean, we ran into a couple of just broken pieces which had to be fixed.
Then we discovered that some of the optics weren't aligned correctly, and it was in a very subtle way. That took us a long time to figure out. And so whenever you're putting something together, you're going to find something that we didn't expect.
An assembly that was scheduled to take 3 weeks took nearly 5.
When you've been working on the machine this long, all the easy problems have been found, and so all that's left is the obscure and subtle ones.
With the delay comes a growing sense of urgency for the BLAST science team.
Because we are very keen to launch as soon as possible to maximize the scientific potential of the experiment. We also require a flight that is as long as possible.
Actually, this is like one big thermos bottle, long, flexible thermos bottle. And the reason we do that is that the helium that came in contact with anything that was anywhere near room temperature would immediately vaporize.
With BLAST finally fully assembled and functional, the last step is to cryogenically cool the telescope's submillimeter detectors to 4.2 degrees above absolute zero with liquid helium, a temperature approximate to the submillimeter radiation it will receive.
Helium gas is so cold going through here, it actually freezes or liquefies the air or in the room. Water comes out first, and that's the snow that you see here. But then it gets so cold that you actually get liquid oxygen, liquid nitrogen up here.
Jim, I'm still not getting AR data.
Before a payload is declared flight ready, it undergoes a dress rehearsal of sorts called a compatibility check.
The line of sight data isn't coming in yet either.
That's an exercise where the payload is taken out and typically hung from the launch vehicle, and the instrument is fired up in its entirety. All of the functions are tested, and when the scientist determines that a CSBF gear is not interfering with what he's trying to do and vice versa, then the payload is declared flight ready.
Here, telemetry, the ability to send and receive data and control functions to and from the payload, is tested and confirmed.
There's two types of telemetry. One is used on relatively short flights that might last anywhere between 6 and 48 hours. That's called line-of-sight telemetry.
Line of sight typically gives the scientists the first initial couple hours of float data that they can thereby look at and see how their instrument's performing.
For longer duration over-the-horizon flights, satellite-based telemetry is used. Of the two, line-of-sight bandwidth is considerably greater.
We can actually go up to about 1 megabit per second and have multiple 1 megabit streams coming down from the payload.
Enough bandwidth to allow scientists to completely reprogram a payload in extreme cases during the first hours of flight.
Okay, thanks a lot, guys. 10 o'clock in the morning.
10 o'clock tomorrow. Okay.
For the flight readiness review.
With the BLAST payload flight ready, the wild card now is the weather. For a country that prides itself on the severity of the weather, Arctic Sweden was in the midst of the coldest and wettest spring in 100 years.
The one plus that it is getting warmer is what was snow yesterday morning finally changed to rain. So a sign that we are at least getting a little closer to spring, but...
Without a full palette of weather data, meteorologist Ross Hayes was feeling an Arctic squeeze.
Showers, and you go 30 miles to the west, the other side of Corunna, there hadn't been any shower activity at all, and the sun's been shining over the lake between here and Norway.
We'll say the global models are fairly good in telling you what the primary weather systems are that will be coming through a general area anywhere on the globe, but to get localized and when the wind will shift, the timing on these events is very questionable.
On top of that, weather conditions for launch must be nearly perfect.
Just put one up at 1,000. That way we kind of get an idea of what the wind speed is and what kind of direction that we're looking at.
The Columbia Scientific Balloon Facility crew uses small tethered pilot balloons to gauge local winds. Surface winds for a launch cannot exceed 6 to 7 miles per hour in the first 200 vertical feet. From 200 to 1,000 feet, the height of a balloon when released, winds must be less than 12 miles an hour.
It's about 14 knots. Yep.
And from top to bottom, launch winds must be in a consistent direction. Any shift in variation or speed during inflation can shred a balloon, a dangerous order for crew and scientists.
Depending on where you are in the world, coming up with that combination of weather can be very difficult, and sometimes there can be delays in launches of a week or 10 days or perhaps as long as 2 weeks.
And with each passing day of bad weather, the BLAST scientific window of opportunity begins to close.
Unfortunately, because of the number of observing constraints that we have, which are related to the viewing angle towards the sun, the latitudes over which the balloon ultimately flies, the duration of the flight. It means that about 8 days ago, we actually lost one of our key science targets.
A target called the Lockman Hole. A gap in our galaxy with very little gas and interstellar dust that presents an unobscured view of the universe beyond.
And so BLAST will still be able to achieve its primary science goals. But there is one unique area in the sky that unfortunately now we're no longer able to observe.
On the overnight, Monday night and the Tuesday, the clouds will begin to diminish, becoming partly cloudy. And then the winds
By
on
week's
Tuesday
end,
will be
the light
north
of
west
improving
8 to 10
weather.
knots. It's during this time that we're looking for the possibility of a launch window right now. We're going to keep close watch and see any other model output I can look at tomorrow to see, grasp this little ridge coming across us.
But the BLAST group knows this opportunity is still more than 5 days away, with the science clock ticking.
We're not going to sit regretting this tomorrow morning, are we?
I don't think so. I think I don't think we're going to have a shot.
The last 2 nights, the science team has observed the wind shut down considerably after midnight, despite the weather reports. And their concern is a closer launch opportunity may be missed.
Where do they need to be?
What do they need to be? I'd say they need to be, for your payload, I'd say they need to be about 8 knots at the max.
Having scientists second guess us during the launch phase is something that we're very accustomed to, and we sort of ignore it as best we can.
Thanks for trying, guys.
You know, there's pressure on both sides, and we're now at this point where we're ready. The experiment's working great, and we're looking forward to the science, and we need to launch within a matter of days to maximize the scientific potential.
And I think we approach that decision with an appropriate amount of daring, but at the same time we have a healthy respect for what a problem it can be if you get too bold in trying to get one of these off the ground.
There's this intermediate ground where, you know, things should go okay, there should be no problem, but we're just not 100% certain.
You know, we'd appreciate it if you guys would bear with us for a few more days. We'll get this thing off, but you know, some of the second guessing and looking at the anemometers and all that stuff, that really doesn't serve any purpose. You know, it doesn't do you guys any good to become junior meteorologists and forecast the weather. That's what Ross is doing. And you know, in the final analysis, we'll get the thing off this weekend. Everything will be fine.
Or will it? How much longer can the BLAST science team hold out?
You're looking good.
Assembly of the BLAST submillimeter telescope was supposed to take 3 weeks. Instead, setbacks cost the science team 2 additional weeks. On top of that, Arctic Sweden's wettest and coldest spring in 100 years. Hardly ideal scientific balloon launching conditions. But just in time, the weekend weather forecast showed promise.
So that east direction is probably our best bet?
Yeah, 68 degrees, 70 at the top of the balloon, still 70 degrees.
And this is for what time?
That's 18Z, 8 p.m.
Though the forecast was optimistic, this launch day initially looked like a no-go.
So you wanna press on? Oh yeah, keep going. I mean, unless you guys see imminent rain. I mean.
Yes, we're ready. Yeah, they're ready.
We're okay.
Well, we're just waiting now for this cloud mass to go away. And when it goes away from us enough, we should be able to establish a solid direction. Look, we got good low-level wind conditions, 3-4 knots, great. So now if we can just get some of this precip to be out, we can launch. I think we might do it today.
It should start settling out in the next 30 minutes.
Okay.
Because this thing's, we're now seeing the back edge of this.
We can't do anything with these rain showers in the area because you can get outflow wind from them, and they just make the direction real squirrely, and you can get gustiness out of it. So that's really bad.
You can see it going to the north of us.
Yes, thank goodness it is going to the north. The patient still has a strong pulse.
He's still alive.
He's still alive, buddy. We're not giving up.
Because of the size of the payload and the 39 million cubic foot balloon, the largest ever launched from Europe, it's important the CSBF crew gets a handle on the prevailing winds in order to set up the flight line in the right direction.
When you have a 900-foot layout, you can't just pick it up and move it that quickly.
When it gets vertical, those winds are going to be affecting the flight train, and those winds are going to be, that's what's going to be dictating what you do with the launch vehicle.
Let's put it on the ground.
Okay, Lars, that should be good.
Lower and upper level winds are gauged by launching and tracking pilot balloons or pie balls.
Throw up another pie ball. They'll ask again. They'll increase the amount to see what the winds are doing, the direction they're coming from the surface up to about 4,000 feet.
But the next pilot balloon shows the winds are beginning to shift and increase.
Now, see, that's not agreeing. That's not agreeing with that pie ball. I mean, because you're looking at this, and this is almost right over my head. It can't be but 3 knots on it. I mean, so that other pie ball run showing 9 knots at 530 feet, it just, unless that little 30 feet, we can get up on this thing and hold it up 30 more feet, and if it goes taking off that way, then...
Oh, we're talking about holding here for about 30 minutes.
The latest progress we got show that at 1 a.m. and 2 a.m., the winds should be lighter. So even if our direction is not quite right, if the winds are light enough, which they should be around 3-4 knots, then it won't matter that much that we are not exactly with the right direction. See, like now, we have like nothing.
Yeah, it's beautiful.
With the weight, improving conditions begin to stall.
I mean, it looks like to me that...
Going away, it looks like it's getting worse.
Well, that's what I'm saying. It looks like to me we better be quick as possible. All right, guys. We're ready.
Stand by. Release the balloon.
That zone is really just all instinct after that. Once the balloon comes out of the spool, you're just operating on instinct, at least I am.
Come on to the right just a little bit more.
And you're watching the flight train as it comes up over the launch vehicle. You're maneuvering the vehicle, talking to the driver, telling him which way to go. The 15, 20 seconds or so that it takes to launch one, it seems like a short time, and it is a short time, but in that 15, 20 seconds, your mind it's got a lot going through it.
All right, stop. Good job, guys.
No, I don't ever get tired of participating or watching a launch. It is quite unique, and it's an experience that we just really, really cherish a lot.
In roughly 2 hours of float time, balloon and payload will arrive at the edge of space, where BLAST, riding westerly upper atmospheric winds, will gather precious data for a full week and return to Earth in northwest Canada.
box. Good job, Mark.
Though the data will take years to sift through, the promised blast holds, in addition to the significance of building existing data sets, is a clearer understanding of the story of star formation and evolution, where they form, how they form, and the overall development of other structure like planets and galaxies in the early universe.
The balloon at float can be seen well in excess of 100 miles. We've had the reports from airline pilots that they could see our balloon and were trying to report near misses to the FAA when the balloon is 125, 145 miles away. From the ground, you can probably see it well in excess of 100 miles.
What's it look like from tomorrow?
Campaign Director Bill Stepp oversees the monitoring, termination, and post-flight recovery of nearly every scientific payload and balloon, from the BLAST submillimeter telescope to this atmospheric experiment that was launched half a world away at the Columbia Scientific Balloon Facility Base in Fort Sumner, New Mexico.
We have a requirement to keep a chase aircraft essentially within 1 hour of flying time from the balloon at any time. What we have is...
While Stepp and his team monitor the westward tracking balloon in real time with sophisticated software.
The safe distance standoff distances are 5 miles in radius around the projected landing point of the payload, and we make sure that there are no populated areas within that area.
A set of statistics is run that tells us what the probabilities are of actually injuring someone on the ground. And those numbers, the probabilities have to be extremely low, like on the order of 1 in a million, before we're allowed to bring one of these systems down.
And then we have a 10-mile radius circle around the projected landing point, and we make sure that we have no major metropolitan areas which have population density outside of the city limits in that area when we terminate.
At the predetermined conclusion of the flight, the aircrew is called in for termination.
They will fly to the location of the balloon, start communications with the FAA, and start getting clearance from the FAA to terminate the flight or separate the payload and the balloon.
After a visual inspection of the projected landing point, a telemetry command is sent, firing an explosive squib that separates parachute and balloon at 120,000 feet in the air. This separation also creates a tear in the balloon, releasing the gas.
The payload descends on the parachute over a period typically of about 50 minutes.
The aircraft will stay in station right around the payload and monitor the descent of the balloon and the descent of the payload.
Once the payload is on the ground, there's a set of sensors that we fly that can tell that it's on the ground, and at that time a set of explosives is fired that separates the parachute from the payload to keep it from dragging in case there's strong winds in the impact area. We have the capability of predicting where a parachute will go from 120,000 feet, typically within 2 to 3 miles. We can tell where it's going to hit the ground within 2 to 3 miles. In over 2,200 scientific balloon flights, we have never even significantly injured a member of the launch crew during the launch process, and there has never been a single public injury associated with any phase of a balloon launch or flight or termination and impact. But that's a pretty significant success rate, and we're very proud of that. Safety is taken very seriously within the balloon program.
In the end, the payload is recovered and returned to the science team to fly another day. There is a place where tracking and recovery is even more predictable, where balloons boomerang back to where they were launched. A place helping to define the next generation scientific balloon. Where is this unlikely capital of modern scientific ballooning? The coldest, driest, and windiest continent on Earth.
We often refer to Antarctica as a natural laboratory. In that laboratory, we're able to field virtually all of the physical sciences.
Despite its reputation for the fiercest weather on the planet, Antarctica has emerged as the hotspot of scientific ballooning for a very interesting reason. Eric Chang is the National Science Foundation's senior U.S. official in Antarctica.
When you mention the Antarctic to the average American, they are entranced. There's a romantic aura, I think, that surrounds the continent itself. And I think they're amazed at, one, the support structure that's here, two, the amount of things that we can get done, the amount of science, the range of science that's done for the dollars that are invested in the program.
The National Science Foundation funds and manages the scientific goals of the United States Antarctic Program, including the operation of McMurdo Station and scientific research across the continent. Few are more acquainted with McMurdo Station and its colorful seasonal population of scientists and support staff than shuttle driver Bill Sunday.
My geriatric adventure. I was 65 when they hired me here. I'm a retired bus driver, and when opportunity came, my wife said, do it, and here I am. Second season.
The most appealing part of his Antarctic summer assignment?
When you first get here, and then all the folks that you meet on the shuttle, all the scientists, support people from plumbers to carpenters to biologists. They're all so interesting and so nice, actually.
As familiar as he is with the scenery, you'd think he'd get tired of it.
No, because you never know what's going to show up here. You can have a penguin come across here in front of you, or a seal out in the middle of the road where you have to stop and take his picture. Always something going on.
Whether it's a driving blizzard or Mount Erebus, the world's most southerly active volcano.
And every picture is different.
Especially a shot of a scientific balloon launch. Sunday's last stop on the outskirts of McMurdo is the scientific balloon base at Williams Field. Scientific ballooning here in Antarctica is the result of a partnership between the National Science Foundation and the NASA Balloon Program.
NASA funds the science, NSF provides the support to that science when they come to the field.
They've perfected the technique of harnessing Antarctica's circumpolar wind. High stratospheric level winds that set up during the Antarctic summer and whip around the South Pole in a counterclockwise direction. Balloons launched into these vortex winds orbit the South Pole, often more than once, making for longer near-space exposure time for experiments. Longer flights mean better science, courtesy of Mother Nature.
Now, what's amazing to me is that you can launch a balloon, put it up in the atmosphere 100,000 feet. You can track it, it goes right around the continent, and some of the most successful launches, we've cut the balloon down within 100 miles of its start point. It's pretty amazing that you can predict and that you can take advantage of this vortex that forms over the Antarctic every year.
Riding this Antarctic vortex in January 2005, a cosmic ray experiment called CREAM set the scientific balloon flight record for duration and distance. CREAM soared for 42 days, completing 3 orbits of the South Pole.
We're hopeful with very minor system modifications that we may be able to fly zero-pressure balloons from Antarctica and take them around 4 or 5 times, resulting in flights perhaps as long as 60 to 80 days, which would just be an amazing opportunity for a lot of scientists.
It's this performance driving the next generation of scientific balloons. Balloons designed to rival expensive satellite-based science at a fraction of the cost.
So NASA envisioned a capability of balloons to fly between 60 and 100 days, allowing to take 1 ton of science instrument to altitudes over 110,000 feet.
Ultra-long duration balloons now in development promise significantly expanded flight durations for scientific ballooning. The ULDB design utilizes advanced materials and a new pumpkin-shaped design. The ultra-long duration balloon is also completely sealed and pressurized to better maintain altitude. More key improvements for quality of science.
In today's environment of fewer and fewer dollars available, that's something we're pursuing just as hard as we can.
And in the biggest quantum leap in scientific ballooning history, NASA plans to integrate scientific balloons into deep space exploration on missions to planets like Mars.
The balloon would be packed on the rocket, launched through its multi-month journey over to Mars. It would come down through the atmosphere, be deployed, inflated, and then float over the surface of Mars, and would allow really vast coverage of the surface, where, say, rovers cover a very small area very, very well. This would allow much better look in a global sense.
Scientific ballooning, the best-kept secret in space science.
It amazes me and frustrates me how few people in the United States know about or even understand what scientific ballooning is all about.
Still a driving and irreplaceable force in the future of space exploration.
We're not blasting into the air with beating the air to death with propellers or screaming through the air with rocket engines or jet engines. Nothing could be more elegant or simple. It's a continuity. I don't think lighter than air travel will ever be obsolete just because it is so perfectly elegant in its application.
In this age of the space shuttle, the International Space Station, and rocketry, scientific ballooning is still relevant and plays an important role in science because it provides for lifting very heavy payloads to very high altitudes and for a fraction of the cost of flying on the space shuttle or the International Space Station, do world-class science.
It's a quiet little engine that always has. And we've been going along providing very economical platforms for scientists since the late 40s. And I really believe that it's the little engine that always will, too.